All right, the first thing we need to do is to get rid of the exponential because it is not exponential that we're focusing on, it is log. So these are log day one. And we're talking about logarithms, all right? So we have this expression that you will see, and it says that a logarithm is read log base b of a, where a is greater than 0, so that's going to mean that it is going to be positive, right? So we've got a is positive and b is also positive. So we're going to have to study the tables below, and then we're going to write an exponential equation that's related to the log equation. So before we get going, let's talk about some vocabulary here. So again, the b represents base. And so even in a log, you will see that the log has the base down here. And even in an exponent, it's the base raised to a power or the exponent, right? So this is the same thing, just in different forms. The a is the argument. So the base to the power is equal to the argument, and then the argument goes here. And a logarithm is just basically what you're trying to do is find the exponent of the base. So you have a base to a power and it equals a number. And we are working backwards and actually trying to figure out what that exponent is. So there are a couple of common things here. So when we're dealing with a common log, it's basically a logarithm whose base is 10. So by default, if you have log and then a number with no subscript, that means that the subscript is 10. All right, so it's kind of hidden there. Whereas a natural logarithm is going to be a logarithm that says ln6 or any number, but what's here as the subscript is an e. So anytime you have ln, the base is always an e. All right, so what we're going to do now is come and take these and rewrite them in exponential form. So we have log base 3 of 27 equals 3. So what that means is our base is 3. We're raising it to a power of 3. And then that is going to equal 27. So that's just exponential form. So we have 2 to the 4th power equals 16. So 2 to the 4th equals 16. 5 to the 3rd power equals 125. 10 to the 3rd power equals 1,000. So again, all we're doing is rewriting. 36 to the 1/2 power. Remember, if you have a fraction as an exponent, it's going to represent power over root. So that means when we have a 1/2 power, it's kind of like, what's the square root of 36? And that's going to equal 6. So 27 to the 2/3 power equals 9. Just check that, right? So the bottom number of the fractional exponent, so this 3, is the cubed root of 27. So the cubed root of 27 is 3, and then this is the powers. 3 squared equals 9. All right, then we're going to have 9 to the 5/2 power, and that is going to equal 243. Okay, they're not asking us if we are right or if we're wrong, we're just rewriting. Okay, these are absolutely correct, but we are just rewriting it. 5 to the 1/2 power is square root of 5. Okay, the way that this works, 4 to the 4/3 power is equal to 4 to the 3/4, which I want you to think about this. This is saying 4 to the 1st power times 4 to the 3/4 power. Okay. no, it's not 3/4. Power over root. So it's 4 to the first times 4, this 3, the cubed root of 4 is 4 to the 1/3 power. And if you were to add 1 and 1/3, you get 4/3. All right, I'm going to try 3 to the 1/5 is equal to 3 to the 1/5. 4 to the -2 is equal to 1/16. 5 to the -3 is equal to 1 over 125. Again, all we're doing is rewriting. 5 to the first is equal to 5. 6 to the 1/3 is equal to the cubed root of 6. And if we were to rewrite that, that cubed root of 6 is power over root. All right. Yeah, I'm on campus. All right. So if we were to take a look at this, it says, based on studying the examples, make a conjecture as to how one would find the value of log of base of A, log base B of A. All right. Then we are going to make 3 conjectures about the value of a logarithm based on the numerical relationship between the value of the base and the argument. So it's saying for us to consider if B is equal to A. So let's take a look and see which of these examples is it. Let me see if I can change my highlighter here. Where is the base and the argument equal to each other? So right here, the log is equal to each other. Is there any other one where we've got looking for where the base is equal to the argument? I think that might be our only one. Okay, so what do you notice in this particular problem right here? That when you have the base and the argument as the same, then the value of the logarithm must be equal to 1. All right, now let's go and look into the other circumstances here. Where the base is smaller than the argument. All right, so let's take a look. The base is smaller than the argument. So let's take a look here. 3 is smaller than 27. 2 is smaller than 16. 5 is smaller than 125. We've got here 36 is bigger. 27 is bigger. 9 is smaller. 10 is bigger here. 5 is bigger than the rad 5. And so we've got, we're looking for where the base is smaller. Okay, I think we've done those. So if we take a look, let's take a look at those answers. And we're talking about what's the value of the logarithm, right? So let's look at all of those values of our logarithm. And if you notice, all of those are numbers where the value of the logarithm, so the answer, is going to be greater than 1, right? So all of our answers up here were bigger than 1. All right, now let me go and highlight a different color here. If the base is bigger than the argument, all right, so the base is bigger than the argument. So we're here, the base is bigger. Okay, so we've got the base is bigger. I missed on that one. Base is bigger. Okay. All right. So what do you notice on those that are green? So remember let's take a look. Let me go back here so I can undo that highlighting. Okay, so that means when we do this, we're looking at an effort to see what's happening with our numbers here. So let's take a look and notice that we've got a negative here, a 1/2, a negative here, a 1/3, and a -3. So if we were to take a look at that, maybe we can make that assumption that it needs to be less than 1, which means it could be a fraction or negative. Okay. All right, so now let's take a look and look here. It says a logarithm whose base 10 is called a common logarithm. It's written like this. Say a logarithm with an unwritten base is understood to have a base 10. Use a calculator to find these values. So you could just literally type in log 5 equals, and let's just make sure that you are getting the right numbers, make sure that you're getting and using your calculator correctly. So some of these you could do that you need to do with the calculator, but this one right here, 10 to what power gives you 100, and the answer is 2. All right, so it says, based on your understanding of the value of a log, what conclusion can you make about the values of the following logs? All right, so take a moment, pause, and let's see what you can come up with. All right, so remember what this is saying. It says a log expression is saying 3 to what power gives you 81. That's always what a log is saying because you're looking for the exponent. So it says find the value of the given log. If the value is not an integer, so not a nice pretty number, between what two integer values do you think the value of the logarithm lies? And then it says, given the expression log of base b of a, use the calculator to find the value of log a divided by log b. So they're taking this and they're saying, okay, the log of the argument divided by the log of the base. Like, what do you get? All right, so remember this is saying 3 to what power, right? So 3 to the x is equal to 81. And so you can rewrite this with a common base, which means x is equal to 4. And if you were to do this in a calculator and write log 81 divided by log 3, what do you get? You get 4. Right? So again, 2 to what power gives you 1 over 8? Well, 2 to the x is equal to 1 over 2 cubed. This 1 over 2 cubed becomes 2 to the -3. So that means x is equal to -3. In your calculator, go log of 1/8 over log 2, and you should get -3. So 2 to what power gives you 9? Well, we know that we can't really figure that out. It's not perfect. So what we need to do is figure out between what two numbers. So we do know that 2 to the third power equals 8, and 2 to the fourth power equals 16. So we know that it is between 3 and 4. Okay, so now let's take a look and see what we would do in our calculator. Log of 9 divided by log of 2, and that is going to equal 3.170. And look, we could have even noticed that it was going to be closer to 3 because it's 8, 2 to the fourth is 16, 9 is closer to 8. So let's take a look at this. 3 to what power equals 36? Well, we know that 3 cubed is 27, and 3 to the fourth is 81. So that means that we are going to be between 3 and 4. And if we were to go log oops, 36 divided by log 3, we are going to have 3.262. Very important for you to make sure you're getting these numbers, right? So 4 to the power of x is equal to 21. Well, I know that 4 squared is 16, and 4 cubed is 64. So that means I'm going to be between 2 and 3. So now let's do the calculator. Log 21 divided by log 4, and that's going to be 2.196. All right, last one. 3 to what power gives you 105? So we've got 3 to the 4th, we know is 81. 3 to the 5th, I'd have to just multiply that out just real quickly. 81 times another 3 is going to be 243. So that means it's between 4 and 5. So calculator work, log of 105 divided by log of 3, and that's 4.236. So what can you conclude about the values of log of base b, a, and then log a over log b? So this is what we refer to as a change of base. Okay, so change of base formula. So remember what we're trying to do is we're trying to find the answer to a logarithm as the exponent. So we can either break them down into exponents that have the same base. For those that you can't do that with, we basically use the change of base formula. And so if I'm given log BA, that is going to equal log of A over log of B. Okay. Try to make this go a little bit faster here. All right, now we're going to be talking about the natural base of E. So if you were in class, I would be doing a little bit of a different demonstration. We'd be taking a look at this expression right here, typing it into Desmos, and finding out what kind of table does it give us if we were to write this expression in terms of x and see what we get and keep plugging it in. So I'm just going to go ahead and do this for you in completing the table. That if we were to replace in with 1, we'd get 1 plus 1 over 1, which is 2, to the first power is 2. So we get 2. And then if we were to do this, we would get 2.594 and 2.705. I want you to pay attention to how big the x's are getting. And I'm only going to go to 3 decimal places from here on out. So no matter how big my x is getting, it seems to be approaching 2.718. So if we think about that, you know how when we go to pi is irrational. That is approximately 3.14159, blah, 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 blah. And then this is going to represent the e. So it's going to be a natural logarithm, and that is going to be approximated as 2.718. All right, so e is a specific number, and we approximate that as 2.7. All right. So notice though that as n, or in our cases our x values, right, get bigger, this value approaches 2.718. This value is called e, and it is called the natural base. So in a logarithm though, with the base of e, it's a natural logarithm and it's written as ln(a). So all of the properties of logs exist for other bases other than e. So it can be, doesn't matter. You just have to specify if it doesn't have a base that's specified, then it defaults to E if it's ln, or it defaults to 10. if it's a log. So what we're going to do is take this expression and we're going to do log A over log B. And then we're also going to do it with ln A over ln B and then see if it matters. So we're going to go log 20 over log 3. And then we're going to put that in our calculator and you should get 2.727. Now we're going to go ln 20. Sometimes your calculators will default with your parentheses, so make sure that you end the parentheses. And you should also get 2.727. Okay, so again, it really doesn't matter if you use ln or log. We just default to log, and we kind of reserve the ln to just represent if you have a base of e. So let's do log of 1/16 over log of 2. And that is going to equal -4, right? That's 2 to the -4 power equals 1/16. And now we'll do it with ln. So ln of 1/16 over ln of 2. And it should also give us -4. Let's estimate real quickly. 5 to what power gives you 15? Well, 5 to the first is 5, and 5 squared is 25. So it's going to be between 1 and 2. So let's go log 15 over log 5 in your calculator. And ln of 15 over ln of 5, and it gives us that same thing. All right, so what can you conclude about the values here and log A over log B and ln A over ln B? So it's still, again, change of base formula. So if you're given log of base B of A, it's equal to log A over log B, or ln A over ln B. Okay. All right, let's take a look over here. Try these. Let's just try one at a time and then check your work over here. It says find the value of x in each of the log equations below by writing the equation as an exponential equation. All right, so we would have 9 to the -2/3 equals x. Okay, so we are rewriting it, and now we are going to simplify that. So the first thing I want to do is get rid of the negative. So that means it's going to be 1 over 9 to the 2/3 power. And so if I rewrite that, I could have this as 1/9, the cubed root of 1/9 squared, which means I have the cubed root of 1 squared over 9 squared. Okay, so we're finding the value of x, but we're rewriting it in an exponential equation first. So remember, if you have ln with no base, it defaults to an e. So e to the third equals x. And now you can go to 3 decimal places. Therefore, x is equal to 20.086. All right, so here we got 3 to the -3 power is equal to 2x plus 1. So I've got 1 over 3 to the third power. I get 1 over 3 to the third power is 27. 2x plus 1, we're just going to solve using our algebra here. We're going to add 1. I'm sorry, just going to subtract 1. So I've got 1 over 27 minus 1. So 1 over 27 minus 27 over 27 gives me -26 over 27 is equal to 2x. I'm going to multiply by 1/2. So I've got negative 26 over 54. But remember what I can do with that. I can simplify that. I'm going to divide each of those by 2. I get negative 13 over 27. All right, let's take a look at this one right here. 25 to the power of x is equal to, remember how we can write this. It's 5 times 5 to the 1/2 power. Okay, so we've got our 5 here and our square root of 5 right here. So 25 to the power of x is equal to, I'm writing 2 over 2, right? That's a 1. 2 over 2, remember when the bases are the same, you add. So it's 5 to the 3/2 power. I'm going to rewrite 25 as 5 squared. So I've got 5 to the 2x is equal to 5 to the 3/2. Bases are the same, so set those exponents equal to each other. So 2x is equal to 3 over 2. Solving for x by multiplying by 1/2. X is equal to 3/4. All right, let's take a look. I've got 2 to the power of x plus 2 is equal to 9. All right. So I really can't do that by converting those bases. So what I can do is I could use my calculator and or also use the Desmos to graph the first equation, y1 equals 2 to the x plus 2, right? And use Desmos again. This time it's the second one, but we don't have to do, this is Desmos. Okay, so you can put y into the first box, y equals 9 into the second box, find the intersection. And you should have x is equal to 1.170. All right, let's do this here. E to the 5th power is equal to x plus 3. Again, they wanted us to solve for x. In this case, what I can do is I can find the intersection, or I can even just subtract 3, because e to the 5th is a number. If I take e to the 5th and I subtract 3, I'm going to get 145.413 is equal to x. Okay. All right, looks like that is it.